Hello and welcome to another episode of CISO Tradecraft, the podcast that provides you with the information, knowledge, and wisdom to be a more effective cybersecurity leader. My name is G. Mark Hardy, and today we're going to look at the underlying technology that many of us take for granted, at least until it malfunctions. And I'm referring to Border Gateway Protocol, or BGP. This is what took out Facebook on the 4th of October in 2021, and their slow recovery was likely due in part to a lack of preparation on how to deal with the BGP incident. Now, this is something that I, kind of knew, but after things hit the fan at Facebook, I decided to dig in and investigate. So stay tuned, and you might be able to become a hero someday when everyone is lost and you can be like Lex in Jurassic Park and say, "It's a BGP system. I know this." As always, please follow us on LinkedIn and make sure you subscribe so you can always get the latest updates. Now, what is BGP? The first document specifying Border Gateway Protocol was from the 1980s. It was Request for Comment 1105. Since then, the protocol has evolved with the internet through 4 generations. We're going to back into a definition in a way because most of the explanations I've seen of BGP assume you know all of these other terms and components, etc. Now, you may, so hang with me, but if you don't, then this should be able to cover all the bases. At its most basic, BGP or Border Gateway Protocol is a protocol for establishing routing between autonomous systems. Okay, that makes sense if you know what an autonomous system is. So what is an autonomous system? An autonomous system is going to be a set of internet routable IP prefixes belonging to a single network or a collection of networks that are all managed, controlled, and supervised by a single entity or organization. An AS, autonomous system, utilizes a common routing policy controlled by the entity. Now, that's a glossary entry from Cisco, and it seemed like a reasonable explanation, although kind of sticky a little bit. So let's kind of take a look a little bit more detail now. So we find then, if we pull that apart, it's a set of IP prefixes, which would mean, for example, 192.168.00/16. There's an IP prefix there, 192.168. Now, of course, that's set aside for special purposes as non-routable. But that's the first part. So an autonomous system will be your set of IP prefixes. They belong to a collection of networks that are all managed by a single entity or organization. And they use a common routing policy. Okay, that's a little bit more helpful because now what I can start to think about it is an internet service provider. Modest size one will probably be considered an autonomous system. And as a result, everybody within that ISP service area, if I want to communicate with my neighbor up the street, I'm not going to have to go all the way around the world to do so. I can probably route within this range of IP addresses that are assigned to this autonomous system. If, however, I want to communicate with somebody who's on a different ISP, then my packets are going to have to traverse the internet and get to another autonomous system, the other internet service provider, and then migrate its way through the inside of that till it eventually gets to the destination. As a result, what we're seeing is that autonomous systems then represent chunks of the internet whereby within each chunk, all the communications that are going to come from outside of there are going to come in and through a common method. Does that help a little bit? So now we're thinking of the internet really is a system of little fuzzy balls, all connected and strung together, so that the center of that ball would be your autonomous system, and then all little fuzz coming out would be the individual systems that are connected to it. Maybe that's a good visual, maybe not. I've seen a couple of maps of the internet and things like that. Remember, Bill Cheswick used to do internet mapping. That's pretty much what he was mapping out as ASNs. Now, when we talk about an ASN or autonomous system number, where do those things come from? IANA allocates autonomous system numbers to regional internet registries, or RIRs. Now, what an RIR is going to be AFRINIC, APNIC, ARIN, LACNIC, or RIPE NCC. These are the major regional internet registries that control assignment of things such as IP addresses and, of course, autonomous system numbers. In the United States, we're with an ARIN. If you go over to Asia Pacific, you'll be an APNIC. If you're Latin America, LACNIC, RIPE, NCC will be over in Europe. Afrinic, of course, you can probably guess where that is. And so as a result, the RIRs are going to further allocate and assign these autonomous system numbers to different network operators. Okay, now what we have is the world chunked into 5 different regional internet registries. Each of them run their own blocks of AS numbers, autonomous system numbers. And the first set of blocks of numbers were 16-bit. So basically from 1 to 64495. It didn't quite go all the way to the end. And those are available for global use. And as I mentioned, that ASNs have evolved over time, so there are now 32-bit AS numbers, starting at 131072, nice power of 2, going up to the 410,000 range. And those are available for global use. Now, there are some that are reserved for use in documentation and sample code. That is to say, if you're going to write up a document, you can say, I can just use ASN 65536, for example. There's a bunch of them. And it doesn't point to anything real. And as a result, if somebody were to try to copy the sample code that you wrote in a documentation, it's not going to send your information off to some other legitimate part of the world where all of a sudden, hey, where do my packets go? Now, there's a whole range of AS numbers that are reserved for private use. And at the very, very end of the range, 2 to the 16th minus 1, 65535, and 2 to the 32nd minus 1 are not to be used. They're legitimate numbers, but they're basically never to be allocated. Therefore, you won't queue an error, but if you put something in there, it's not going anywhere. All right, so there's this whole universe of numbers that are basically going from 1 to about 65535, and then 131072 all the way up to about 4.2 billion. Huge number of potential blocks of autonomous system numbers. Now, if we did a little bit of digging, we can take a look at some of the tables and see who are arranging those and who owns them and who sets them out, etc. So if we look at the IANA assignment, we can then find out who gets what. And we'll see, for example, that if we take a look at autonomous system numbers 1 through 1876, that these are assigned to by Aaron, all right, North America. ASN 1877 to 1901 are assigned by RIPE NCC, so it'll be Europe, and so on. And there's big chunks of autonomous system numbers that are assigned out. And you can look up the blocks if you're so inclined. Now, what I thought was interesting is if you take a look at ASN 2, it was allocated to the University of Delaware over 30 years ago. Wow, I didn't realize that they were in that early, but University of Delaware has got ASN number 2. And I could look up the assigned CIDR blocks. There's a couple tools out of there. Team Cumlery has a tool. Robtex has a tool. I've got IP addresses. I should probably put them in the links here. But what I can do is take a look at Autonomous System 2, AS2, and look up, and it has a block of IP addresses, 128.4.00/16. So anything that begins with 128.4 is assigned to the University of Delaware, 65,000 plus or minus IP addresses, and it'll come in through Autonomous System number 2. That means anything within that address range, if you're going to transmit to it from any place in the world, has got to come to AS2, at which point it says, hey, I'm the gateway to all this stuff, in you go. And I looked it up for my current location, my internet service provider. My autonomous system number is 33363 for what it's worth. And yes, there is an autonomous system number 31337, and it's registered to Elite, ELEET networks in Sweden. So good for them. Now, I can also look up other IP address ranges associated with University of Delaware, and I find out there's other autonomous systems, and they have peers. And a peer would be another ASN that they can share with. And we'll get into peering and then the relative hierarchy in a couple minutes. But if you repeat this thousands of times, you can map the allocated IP address space to an associated ASN and essentially map out the entire internet. And essentially, this is what has to be done if you're going to connect everybody. for an arbitrary IP address to connect to another arbitrary IP address on the internet, there has to be a route that gets from one point to the other. And the BGP Border Gateway Protocol is what is used to communicate between these autonomous systems to set up these routes. Now, as of the 5th of October, 2021, there are 106,562 ASNs. The United States has over 29,000 of them. North Korea has one. And if you need to, you can request an ASN at the aaron.net website if you have legitimate reasons for doing so. Now, we can view the internet as comprising of thousands of autonomous systems that connect to each other, the internet backbone, if you will, and then millions upon millions of IP addresses connected to individual ASNs that fan out to include everybody that's on the internet. Now, on the RobTech's website, they've got a nice little explanation which I'd like to share. It says an autonomous system is a network sharing the same rules on how it should connect to the rest of the internet, or a routing policy. Okay, we kind of knew that already. As such, it functions as one independent subsection of the internet. This is done to make internet routing more comprehensible because each autonomous system is assigned a specific number, ASN, that can be used in Border Gateway Protocol routing. And now we can define paths to follow. And most holders of autonomous system numbers, pay attention, have multiple uplinks where traffic can be diverted in case of a failure. As such, no single point of failure can bring down the entity. And just like IP networks, one big ASN can have several smaller ones behind it, making global routing scalable. As really other networks only have to keep track of the larger ASNs, which will act as a front for the rest. So what happens then is we're starting to see that these big chunks of the internet, as defined by autonomous systems, allow us to, if you will, take a shortcut. Similar to if you look at a zip code, if you know the first number of a zip code, then you know what part of the country it's going to go to. If it is a 0, it's going to go to New England. If it's 1, it's up around New York, Pennsylvania. If it's a 9, it's out west, California, Alaska, Hawaii, things like that. And as a result, you can go into it and get some more information or some capabilities to get things going in the right direction. Their routing tables then define which routes traffic should go through, because what happens is Border Gateway Protocol defines different preferred or reachable paths across different networks. And these autonomous systems will exchange information with each other so that they can say, hey, I know how to get to so-and-so, and I can get here and I can get there. All right, great. Let me copy that table. Oh, by the way, I know how to get to here and here. And what happens then is different autonomous systems begin to talk to their neighbors or peers, at which point then they're able to know what path to follow. And as a result then, with the classless internet domain routing, or CIDR, where we have some part of an IP address slant and then the number of bits that are allocated to that grouping, then what happens is your routes within the ASN can communicate internally with an interior Border Gateway Protocol, but externally they're going to be using the regular Border Gateway Protocol. Big, huge chunks, smaller chunks, and then ultimately individual IP address blocks. Now, Cloudflare has a description of BGP that is a nice analogy. It's the postal service of the internet. It's going to select the best possible path for data travel, meaning it's usually going to send data hopping from one autonomous system to the next. They continue the analogy by stating that autonomous systems are like post office branches. Even though a town might have thousands of mailboxes, all that mail has to first arrive or depart to its own local post office. Now, because the internet is not static, new autonomous systems arrive and old ones depart. And thus, each autonomous system must maintain current information regarding new routes as well as removing some obsolete ones. And they talk to each other through some sort of a peering session where each is going to communicate with its neighbors and share best routing information. Now, routing on the internet is not just about the shortest trip. I mean, some networks will charge for use, and you might not want to route through other countries, for example, if you're concerned about national security. And so just like Google Maps, where you can select no tolls and get a routing to get you from A to B, routes may be selected based upon other criteria other than just the shortest trip. Another analogy that was offered by Cloudflare is external BGP is like international shipping, has very precise standards and guidelines. Internal, well, you can do your own. they point out a couple places where, well, things have gone wrong. In 2004, a Turkish ISP called TTNet accidentally advertised incorrect border gateway protocol routes to its neighbors. The routes claimed that TTNet itself was the best destination for all traffic on the internet. Well, remember, these ASs are going to share with each other and appear, hey, guess what? I got a tip for you. And then as these routes spread further and further to more autonomous systems, a massive disruption occurred, creating a one-day crisis where many people across the world were not able to access some or even all the internet. Fast forward a couple of years. In 2008, a Pakistani ISP attempted to use a BGP route to block Pakistani users from visiting YouTube, but they accidentally advertised these routes with its neighboring autonomous systems, and then the route quickly spread across the internet's border gateway protocol network. And these routes sent users trying to access YouTube to a dead end, and they were inaccessible for several hours. What we're starting to see then is we've got a system that is really kind of built on trust, designed many, many years ago, but there's ways to breach that trust. There's also a practice called Bgp hijacking, which doesn't always happen accidentally. In April of 2018, attackers created bad BGP routes to redirect traffic that was meant for Amazon's DNS service. Attackers are able to steal 100,000 plus worth of cryptocurrency by redirecting the traffic to themselves. Now, incidents like these can happen because the route sharing function of border gateway protocol relies on trust, and autonomous systems implicitly trust the routes that are shared with them. And if a peer announces incorrect route information, whether intentionally or not, traffic goes where it's not supposed to, even potentially with malicious results. Now, we're not quite yet at Facebook outage, but hopefully you're starting to kind of you're starting to figure out what's going to happen, right? Now, these autonomous systems send BGP information in accordance with request for comment, or RFC 4271. That's BGP 4. They'll exchange update messages with other systems. And when you receive these update messages from your peers, you begin to construct a graph of connectivity for reachability. And then if there are any loops, you can prune those, get rid of them. If you have policies that say, yeah, I don't want to go through that country, then I can eliminate that. And then store these routes in what are called RIBs, or routing information bases. Now, RIBs have three parts. It's got the input queue, if you will, which is for all the incoming update messages from other BGP speakers. And this ultimately ends up as an input for the algorithms who are going to decide a route. There's a local RIB, routing information base, which local routing information within your assigned systems, because of course you still have to move things around within the AS. If you're an ISP, you might have thousands or tens of thousands of systems. They don't all go through one big, gigantic switch. And then there's a third one which stores information, the outbound, for sharing with peers through outbound update messages. Now, a routing table is going to accumulate these routes to directly connect the networks, static routes, routes learned through interior gateway protocol, and even from border gateway protocol. And now each of these systems are building up their own routing table. Now each autonomous system, because it's, well, autonomous, knows what to do. It's a full up round on the internet where it can go ahead and talk to anybody it needs to. Pretty cool. Now, border gateway protocol, though, seems like that's like a layer 2, layer 1, layer 0. I mean, no, it runs using Internet Protocol, which is the core protocol of the internet, using a layer 4 TCP, port 139. TCP IP is the core protocol of the internet, so why not put it there? Your messages are no more than 4K long, depending on the content. And if you looked at a message, it would either be an open, an update, a notification, or a keep alive. Kind of like a SYN, when you're going ahead and doing a TCP connection, the first message in BGP is an open message. Instead of getting back a SYN-ACK, you'll get back a keep alive, which is an agreement to keep the connection open for the requested hold time that was in the open message. At that point in time, the BGP peers can exchange update messages. And with that, each system begins to construct a graph that describes their relationship to the various autonomous systems. Now, update messages can advertise feasible routes. Hey, I got a new way to get here. Great. Or withdraw unfeasible routes. Hey, this doesn't work anymore. Get rid of it. Okay, because you said so. Remember, it's all based on trust. And then notification message, the fourth kind, it's really error reporting. And they indicate, hey, what you sent me was out of range, didn't work, etc. By the way, I'm closing this session. And as a result, then, there is a constant communication going on between autonomous systems. So now, if we think about it and we follow the packet, let's follow a packet as it moves from hop to hop through the internet. Sender can look up the destination through DNS. Now, it's a separate issue. I'm not going to get too far into DNS, but ultimately we're going to go to the root server, figure out where the authoritative server is, go to the authoritative server, and get back an IP address that corresponds to a particular domain. The first hop may be from a local non-routable IP address inside a local network. So 10.0.1.1.101. Okay, it goes to the local switch. The switch, 10.0.1.1.100, could then connect the gateway. The gateway may be 10.0.0.1. We'll do a network address translation to the externally facing IP address that is leased from the internet service provider, maybe something like 1.2.3.4. And now the local internet service provider may move that packet through a few systems before it reaches the edge, if you will, the autonomous system, the router that has the border gateway protocol route information. At that point, the best route is selected for the proposed destination, and the packet is sent off into the void outside of the ISP, hopping from system to system based upon the best path calculated for the destination. And when the packet reaches the destination ISP, its autonomous system, the process is reversed until it's eventually delivered to the destination. All right, sounds pretty straightforward. But now we understand a little bit more about, we know it goes A to B to C to D like a trace route, but why does it go A to B to C to D? Now you know. So let's go on to Facebook. Now, a disclaimer here. Most of what I learned about BGP I researched this past week. And frankly, I thought it was too much being in the weeds for a CISO. But after watching a major enterprise go hard down for hours, I realized that as CISOs, we all need to have a working knowledge of how BGP works, just in case we find ourselves in a similar situation. So that said, what I offer may be a little bit of conjecture. It may be wrong. I'm also, however, going to really rely heavily upon statements made by Facebook. And so we'll assume that their information, since they're a lot closer to the problem, is accurate. But let's see what we might be able to reconstruct. So I mentioned a couple tools earlier, and I found that Facebook is assigned a couple ASNs, 32934 and 63293, representing, no surprise, thousands of IP addresses. Now, on Facebook's website, there is an article entitled More Details About the October 4th Facebook Outage by Santosh Janardhan. And here's what the author offered. He said that in the day-to-day maintenance of this large, thousands and thousands of routers and huge enterprise at Facebook, that from time to time, engineers need to take part of the backbone offline for maintenance, maybe replace a fiber line, add more capacity, etc. Well, during one of those routine maintenance jobs, a command was issued to assess the availability of global backbone capacity. But it was set the wrong one, and they unintentionally took down all the connections in their backbone network, effectively disconnecting Facebook data centers globally. Now, this is their words here. Our systems are designed to audit commands like these to prevent a mistake like this, but a bug in that audit tool prevented it from properly stopping the command. So what do you think happened? Sounds like a BGP message that went out. And again, this is my conjecture. That was an update that withdrew an unfeasible route. And instead of saying, hey, take down this one system or take down this one thing, they accidentally took down their entire AS. Well, this compounds now because it created a complete disconnect of all their server connections between the data centers and the internet. And as that message that was advertised that went out to the peers, to the other autonomous systems, they said, oh, get rid of this. All right, thank you. All right, get rid of this. And before long, it gets deleted pretty much throughout the whole world. Now what? Everybody's disconnected. You don't even exist anymore. But that's all right. We still have DNS, right? We can still have somebody look up an IP address, and if they still have cached that BGP information, maybe you can still get there. Except for the fact that they run their own DNS servers. And so now those DNS servers are authoritative name servers advertised to the rest of the world. But what had happened is with the BGP advertisements meant that the DNS servers kind of got taken out as well. And what happens then is the way it's set up for the reliable operation, their DNS servers will disable border gateway protocol advertisements if they can't speak to the data center saying, well, it's an unhealthy network connection. Tube it, get rid of it. And in the recent outage, according to Facebook, the entire backbone was removed from operations, basically making everybody declare themselves unhealthy. They withdrew all the BGP advertisements. The end result, the DNS servers themselves weren't even reachable. And therefore, it's impossible to find the rest for the rest of the internet to find your servers. Okay, so this is a compounding problem. And now the primary network access is down. The out-of-band network is down. And so now what happens? You got to put engineers and drive out to data centers and try to debug the systems. But they're designed with a lot of physical security in mind, system security. They're hard to get into. Now, we've heard rumors about people taking grinders to cut off cage doors and things like that. I can't confirm or deny them. But those systems are designed to be difficult to modify even at the console because there was never expected a reason to ever have to sit at the console. So as a result, it took several hours of physically getting to places and turning things back on again. But you couldn't quite turn everything on all at once because with the total drop in connectivity, nobody going to Facebook, they indicated their power usage had dropped by the tens of megawatts. And if all of a sudden you brought everything up right away, that surge could go ahead and take out everything from your electrical system. So they had to kind of walk it back on. What they find, though, is that as a result of a scenario that they hadn't really thought about because they do storm drills and they simulate system failures and but in the end, they were able to get back up and running within the same day, which is pretty good, even though they never, ever had a simulation that way. So Facebook, between a combination of BGP, probably a bad advertisement going out, taking that off, the DNS server saying, hey, I can't get to there, so I'm no longer going to respond to that. That's going to take that down. And then cascading result was nobody could get to DNS servers from Facebook, and you couldn't get to the ASs from Facebook because it looks like the route paths were all deleted. Everything had to kind of be rebuilt from scratch. Now, once you come back up, it's like there's a brand new Facebook here, still using the same IP addresses, but that advertisement then has to propagate from AS to AS to AS so the rest of the world can use it. So let's think about it. As CISOs and as security leaders, what can we learn from this? Although border gateway protocol routing is probably an upstream problem, you cannot outsource accountability to your ISP if your connectivity goes down. You can't go ahead and go to the boss, go to the board, or go to your customers, go to the lawyers and say, well, yeah, the reason we didn't meet our requirements and we didn't meet our service level agreements is, well, blame it on the ISP. Nope, you're responsible as a security leader to think about these scenarios, which may mean you might want to have a primary or a secondary, even a tertiary ISP. Well, how do I know whether they're vulnerable? Guess what? We've got some basic tools. And using those basic tools that are available online, you can assess the resiliency of your uplink and consider whether a secondary or tertiary, as I said, is a wise precaution. I know that for one of my clients that I work with as a CISO, that we have a high-speed fiber link, and then we got a alternative copper link at a much lower bandwidth. And they go in different directions coming out of the building. Why? In case a backhoe takes out the fiber or something goes wrong heading north, we're still up and running going south. Now, heading south, I don't have a ton of bandwidth. I'm not going to be able to support 100 people watching cat videos, but I can support some of the basic stuff that needs to take place with email. And as part of our incident response plan, we've already got a backup for that, which says what? Every employee is issued an iPhone with a data plan. Take your laptop and then fire up your iPhone, plug it in so the battery doesn't go down, and then run off of that. We'll pay for the data. And now what happens is you've really cut down the amount of bandwidth that has to go in through there. Now it's a different environment, and we're not going to talk about accessing servers and things like that. But the point is you can keep up and running if you plan ahead a little bit. So consider in your drill and exercise scenarios BGP loss, DNS loss of upstream, some of these other new scenarios that if you're able to do that, you might be able to build in a little bit more resiliency in your planning, and you'll be more effective in the event that something goes bad. Okay, so that's BGP. Hopefully it wasn't too deep of a technical dive. As I said, I didn't know a ton of it a week ago, so I did a bunch of reading. The RFC is only 101 pages if you ever want to get way into the detail. But nonetheless, I think by now you have a better feel for how it works. And heaven help you, I hope you never have to worry about having this level of outage that hit Facebook. But if it did, at least you kind of get a couple guesses of where you might have to go. And knowing that the primary and secondary access methods to servers and systems and even facilities may be inaccessible, start thinking about how do you actually have a workaround, and then you'll be able to do better. So that's it for this week. A little bit shorter, but anyway, that's as much as I want to go into, and I don't think you care too much more. But this is G. Mark Hardy from CISO Tradecraft, encouraging you to share this with your friends and let people know where you learn your good stuff. Thank you so very much, and till next time, stay safe out there.